Good morning, everyone. My name is Laís Brazaca. I'm a professor at University of São Paulo, and today we're going to talk about the use of biosensors for monitoring clinically relevant molecules. So for discussing this, I've selected two of our recently published works. The first one was developed along with two other Brazilian universities, UFSCar and UFO, and it is about the development of a new conductive filament for printing, for 3D printing electrodes and using them as sensors and biosensors. So first of all, why would we want to 3D print electrodes? For me, the most important advantage that this technique brings is the fact that it's extremely versatile. So you can not only produce your own electrode materials, as we did in this work, and you're going to have the details in a second, but you can also change designs very easily. And everything is lab made. So you can have these printers in the lab. They're currently accessible, not that big. So then you can tune everything, the design and the materials very easily and very quickly. Also, the relative cost of fabrication is low, and you can also make the electrodes already integrated into the structures you desire. So for example, you can print a vial and place electrodes in there. So you can adequate everything to your specific purpose. So everything is custom. The most used technique for 3D printing electrodes is called fused deposition modeling, and it is the technique that is most used for 3D printing in general, in which you do have a filament that is heated and then it is deposited by a nozzle. And this is done in a layer by layer fashion. So when this first layer cools down, it hardens, and you can add the next layer on top. And then you can print the device you wish in 3D. Specifically for sensing, we usually use a mix of conductive materials, usually graphene or carbon black, and some polymers as the filament. So you still have good mechanical properties, filaments that are adequate for 3D printing, and you have conductive materials. Currently, we do have a bunch of commercial filaments that can be used to produce electrodes. But the main problem with these filaments is that usually you do require pre-treatments to use them. So some filaments, they do not have a lot of conductive material on them, so almost around 8% in weight is made out of conductive material, and then you do need these pre-treatments in order to expose the conductor, to have more conductor on the surface, or to make the electrodes more porous, and again, you will have more connection to the conductors. This can be done by mechanical polishing, by electrochemical activation, immersion in solvents, and a few other methods, being the electrochemical activation very common. But these processes can damage the electrodes. They are time-consuming and can also generate chemical residues. So it's nice to avoid them if we can. So that's why literature is currently pursuing filaments that do not require any pretreatment. So in this work, what we have done is we have developed a new filament composed of basically graphite and PLA, so polylactic acid, with an enhanced amount of graphite, so around 40% in weight, making this filament not require any pretreatment to be used as a sensor and as a biosensor, as we will see in the next few slides. So first of all, how are these filaments produced? Here on the left side of the slide, you can see a summary of the process, and here on the right side, you can see a video. So first of all, what we do is we mix the polymer and the graphite in a reflux bath with oil. So we add the graphite, and we use a temperature of around 70 degrees Celsius. Then the polymer is added, and once everything is mixed well together, we add everything to ethanol, and you can see that it gets recrystallize it. Then everything is washed with ethanol using a filter and a funnel. And after that, we can dry the composite. After dry, we break it into smaller pieces using scissors and our own hands. And these small pieces can then go to the extruder to produce the filament. So this is the filament that will be used for 3D printing the electrodes. So then the filament is added to the 3D printer, and now we're printing an electrode. After printing, the electrodes get some grooves in them due to the printing process, and then we do some mechanical polishing just to remove these grooves and to make the surface smooth. So this is the working electrode. We construct the other two electrodes in the same way, so reference and counter are made in the exact same process. So we can just connect the potentiostat and perform the measurements. Okay. So first of all, we have optimized the composition of the filament and characterized it. So here on the left, you can see some cyclic voltammetries using ferrocyanide as a redox probe with different graphite loadings. So you can see that as the graphite loading increases, we do have lower peak separation and also higher peak current. But the problem is, if you enhance the graphite loading too much, you will have a brittle filament. So 50% was already very brittle. So then the optimized condition was 40%. We still have a good current and a good peak separation. So this filament was chosen as the ideal one, and this will be the one used for further experiments. So 40% in graphite loading. We also characterized the filaments using Raman spectroscopy, and you can see the peaks related to graphite are present on the surface, both for the filament produced, which is shown in black, and also for the printed electrode, which is shown here in red. So D, G, and 2D are all present in both samples, showing that there is some graphite in the surface, which is what we desire to acquire. We also did some microscopy. So this is SEM, scanning electron microscopy, in an enhancement of 8,000 times, sorry. And we can see that there are graphite flakes all over the surface we studied, again showing that the composition of the filament was adequate, was as expected. So as I mentioned, the main feature of this filament is that it does not require any electrochemical pretreatment, just some sanding to remove the grooves from the 3D printed electrodes. So what we did here is we compared the performance of the developed filament with the ones already present in the market. So we did this with and without electrochemical pretreatments. The electrochemical pretreatment applied was using NaOH and applying some fixed voltages for 200 seconds. And this redox, the redox probe used in these CVs was ferrocyanide. So you can see from the voltammograms that without treatment, so this is voltammogram A, without any pretreatment, the performance of the developed filament shown here in black is much superior to the commercial filaments without any treatment. So after treatment, we can see that the developed filament is still superior, so we have higher peak currents than the commercial ones, but you can see that there is a clear improvement in its performance. And here on the voltammogram on the right, you can see that there is very little change before and after treatment of the developed filament, showing that a lot of the graphite is already exposed on the surface. So this shows that we are getting exactly what we wanted with this composition. So for applications, for sensing applications, we did as a model analyte the detection of uric acid So uric acid is a product of the metabolism of purine, and it is a key antioxidant in the body. It is related to a bunch of diseases, but especially its increased levels in serum are related to the development of a series of conditions such as hypertension, coronary heart disease, cardiovascular stroke, cerebrovascular accidents, and more. So right here, on the right side, you can see the oxidation of uric acid using the developed filament and the commercial filaments, treated and untreated. So we can see that the untreated filaments have very poor performance. The treated commercial filaments have a better performance, but the filament developed by us here in black has shown superior performance even without any pretreatment. Here's a calibration curve using DPV, so differential pulse voltammetry, from 0.5 micromolar to 150 micromolar. We got a very nice linear range with a limit of detection of 0.07 micromolar. So this limit of detection would allow us to detect uric acid both in serum and in urine, and we did test the sensor in synthetic urine, which contains a bunch of organic molecules and a lot of salt, and we got around 90% of recovery, which shows that the sensor is also adequate for more complex environments. So we also wanted to do some immunosensing with this filament, and doing some FTIR experiments, we found out that we do have some carboxylic acid groups in the surface of the sensor. So we can use EDC and HS coupling to add antibodies to couple them covalently to the surface, and we used some BSA to block the remaining surface and groups that were still active after antibody mobilization. So we used this immunosensor to detect spike protein from SARS-CoV-2 as, again, a model analyte. So here you can see some voltammograms in the absence of S protein that is shown here in black, written in BSA, and some voltammograms showing the difference in the signal after different concentrations of S protein are added. So we can see that the voltammograms, the peaks here from, again, ferrocyanide, decrease with the increase of S protein due to the blocking of the surface. So if we plot the delta of the current versus the concentration of spike protein, again, we do get a nice linear curve with an LOD of a few nanomolar, which is quite good. Okay, so now I'm going to shift for our second project that is related to the development of immunosensors with carbon electrodes that contain some electrodeposited gold nanostructures in different shapes and different sizes, and we study what's the influence of these nanostructures for the detection of S proteins from SARS-CoV and SARS-CoV-2. Again, this work was developed not only by USP, the university I'm from, but also this was done along with UFSCar. So first of all, why do we want to use gold nanoparticle in electrochemical biosensing? So usually these particles promote an enhancement in electroanalytical activity. So they do facilitate electron transfer, and they do provide catalytic activity for the oxidation and reduction of many different species. Also, we do have a very high surface to area ratio, which allows us to increase the number of bioreceptors we can immobilize in the electrode, and allows the easy modification on the electrode surface using thiol groups, for example. And the analytical performance can be tuned depending on the nanoparticle nature, size, shape. So in this work, we have decided to study different conditions from a protocol for electrodepositing gold nanoparticles on an electrode surface and its influence on the development of a immunosensor. So how did we do this electrodepositing of gold nanoparticles? So first of all, we had a screen-printed electrode produced by us in PET. So it was a flexible electrode, all made of carbon, and then a reference electrode was painted with silver chloride ink. So using this electrode, we have electrodeposited the gold nanoparticles using a constant potential and different times. So we use it 9 seconds, 30 seconds, and 90 seconds. So we can see with the naked eye that we have an enhancement in gold deposition that is extremely clear with 9, 30, and 90 seconds. If we do SEMs of each electrode, we can also see that before gold deposition, we do not have any visible nanoparticles as expected, not visible gold nanoparticles as expected. And after doing the deposition for 9, 30, and 90 seconds, we do see an increase in the size of the particles electrodeposited. For 9 seconds, the particles are spherical, and for 30 and 90 seconds, we do have more irregular shapes with some sharp edges. We do have a very large increase in the diameter of the particles from 143 to up to almost 800 nanometers for 90 seconds. So how do these relate to the performance of the biosensor? But first of all, we did some electrochemical characterization of the modified electrodes. So we can see that with the increased time of electrodeposition of gold, we do see an increase in the peak related to the redox process of ferricyanide as expected, and we do see a decrease in RCT, showing that we do have more conductive surfaces. So looking at this, maybe it could seem like the 90-second electrode would provide the best performance for immunosensing. Okay, so after characterizing the electrodes containing the electrodeposited particles, we have attached the specific antibodies to S protein so that we would build our immunosensors. So what we did for that was we first added mercaptoacetic acid so that the thiol group would bind to the gold, leaving carboxylic acid groups available for interaction. We then followed the binding with EDC and NHS and made the covalent binding of the antibodies with their amino groups. As previously, we did the blocking with BSA, and then the sensor was responsive to the desired S protein. Okay, but building calibration curves using IES measurements. So here we're assessing the charge transfer resistance of our electrode. We can see that for 9 seconds, when we use S protein, meaning our target, we do have an increase in RCT with increased protein concentration, as we expected, because the surface of the electrode is being blocked. When we use a control molecule, such as BSA, we do not have this increase. So 9 seconds, deposition time is working exactly as expected. If we go to 30 or 90, we do see that the behavior is quite different. So for 30, we still have some differentiation between S protein and BSA, but for 90 seconds, the curve starts to overlap. This can clearly be seen using this graph on the bottom that shows that the sensitivity of the curve for S protein, it decreases from 9 to 30 to 90 seconds of electrodeposition time, and for BSA, the sensitivity increases. So the conditions that provide the most difference between the two proteins is 9 seconds, and this was chosen as the ideal one to go forward and to do some studies on actual biological samples which are used for diagnostics. So what we did here is we used human saliva for building the calibration curves. So right here you can see the IES spectra. As previously, we do have an increase in RCT with increased concentrations of S protein, but we can also see that BSA and S protein curves are quite close right now. This is probably due to the presence of non-specific interactions because there is a lot of other molecules in the saliva. But we can still differentiate between the two species. We also did add some inactivated SARS-CoV-2 viruses to the saliva, and we were able to differentiate between negative and positive samples, showing that this could be an alternative method for diagnostics. Okay, so this is what I wanted to show you today. You can know more about both of these works in the published papers that are attached to this meeting. I would like to thank the organization committee of the event for the invitation. It was a pleasure to be here today. I would like also to thank some of the groups that were mostly involved in developing these biosensors, which is Biomics from University of São Paulo and LSNano from UFSCar, which are represented here by Professor Carrilho and Professor Bruno Genegitz. And I would like to thank FAPESP for the financial support. Here's my contact information if you would like to talk to me. Thank you very much.